Today we will be discussing about the binary search. This is one of the divide and conquer algorithm. First, let's begin with explain about how does divide and conquer algorithm works. It works by according to the following general plan. Firstly, a problem is divided into several subproblems of the same type, ideally of about equal size. The subproblems are solved typically recursively, though sometimes a different algorithm is employed, especially when subproblems become small enough. If necessary, the solutions to the subproblems are combined to get a solution to the original problem.
Assalamualaikum, I'm Israt Jahan from BITP S1G1. So today my part is binary search algorithm introduction. So binary search is a divide and conquer search algorithm. It uses O log n time to find the location of an element in a search space, where n is the size of the search space. Binary search works by halving the search space at each iteration after comparing the target value to the mirror value of the search space. To use binary search, the search space must be ordered in some way. Duplicate entries cannot be disambiguate, though they don't violate the binary search property. The next, working of the binary search algorithm. The first thing to note is that a binary search algorithm always works on a sorted list. Hence, the first logical step is to sort the list provided. After sorting, the median of the list is checked with the desired value. If the desired value is equal to the central index node, then the index is returned as an answer. If the target value is lower than the central index tail of the list, then the list right side is ignored. If the desired value is greater than the central index value, then the value left half is discarded. The process is then repeated on sorted list until the target value is found. Let's see an example question. So let's imagine an economist, a pretty bad one though. He was given the task of finding the equilibrium price, that is the price where supply equals to demand for rice. But he needs to remember the higher price is set, the larger the supply and the lesser the demand. As this company is very efficient at calculating market forces, he can instantly get the supply and demand is unit of rice when the price of rice is set at a certain price P. So he is allowed to call functions get supply K and get demand K, which will do exactly what is stated in the problem. So let's see our next slide. The following pseudocode demonstrates the uses of binary search for the example level. So here our search space is from 1 to 10 to the power 17. Thus a linear search is infeasible. However, notice that as the K goes up, get supply K increases and get demand K decreases. Thus for any X is greater than Y, get supply X minus get demand X is greater than get supply Y minus get demand Y. Therefore, this search space is monotonic and we can use binary search. So, this algorithm runs in O log n 10 to the power 17 time. This can be generalized to O log s time, where s is the size of the search space, since at every iteration of the while loop, we held the search space from low high to or either low mid or mid high. Thank you.
Hi, my name is Cecilia Chong from BITS S1G2. My metric number is B0319103990. The algorithm that our group choose is binary search. Now, I will present about the picture diagram to explain the step-by-step of process flow for binary search. Before this, in my presentation, I will look 3 types of example. First type is target same as middle. Second is target less than middles. And the last one is target larger than middle. It is because there is some difference for these three types of example. Before we start to do binary search, we need to ensure the array is sorted. I will use this sorted array to explain the step. First, I will explain the type 1, which is target equal to middle. Now, the target that we need to find is 46. First, we need to set the first element of sorted array as start. So we can see in the diagram, we use the arrow of start, put it in at the index 0. We also set the last element of the sorted array as n. So now you also can see the arrow of n is located at index 6. Next, we will find the middle. We use this formula to find the middle. We use start plus n. It means that we use index 0 plus index 6 divided by 2. We will get the index 3. The index 3 now will present the middle. So we will put the arrow of middles at index 3. Now we can compare the value of target, which is 46, with the value of middle, also is 46. So as we can see, we can conclude that we found the target for one loop only. Next, I will explain the type 2, which is target less than middle. Now the target value is 27. We repeat the process for the first and second, which is we set the first element of sorted array as start. We also set the last element of sorted array as n. So we can do this in a table to see clearly. Okay, we can do the table with loop, start, middle, and end. For the first loop, we can know that because just now we already set the first element, which is hold the index 0 as the start, and we set the last element, which is index 6 at end. So we also will use the formula middle equal to start plus n divided by 2. So we use 0 plus 6 divided by 2, we'll get 3, index 3. So now index 3 is the middle. So therefore, we compare the target value, which is 27, with the value of middles, which is 46. 27 is smaller than 46. So we need to use this formula, these two formula, to do the second loop. So inside the second loop, we can see that the n will become changes. So we use this formula, n equal middle minus 1. So we use the 3 minus 1 become 2. So now the arrow of n will from index 6 move to index 2. After we move the arrow of n, we need to change for the arrow for in middle. So we use the same formula, middle equal start plus n divided by 2. So we use the start is index 0 plus the index for n is 2 will become 0 plus 2 divided by 2 will become 1, index 1. So the middle, the arrow of middle will move from index 3 to index 1. Then after we move the arrow of middle, we will compare the value of middle, which is 27, with the target value, which is 27 also. As we can see, we can conclude that we found the target using two loop. Lastly, I will explain about the type 3, which is target larger than middle. Now the target value is 60. We also do the first 3 steps for the for this binary search. First, we will set the first element of sorted array as start, set the last element of sorted array as n, and we will use the formula middle equal to start plus n divided by 2. So we also can see clearly in this table. We use the loop for the first loop. We can see that start is at index 0, n is at index 6. So we use the formula to find the middle. Middle, we use 0 plus 6 divided by 2. We will get index 3. So middle now is in the index 3. We also can see in the diagram, now the middle is in the index 3, which hold the value 46. We compare the 60 with the 46. 60 is larger than 46. Therefore, we have some changes for the start value. So we use this formula, start equal to middle plus 1. So now we can see in the second loop, the start we use the middle plus 1 will become 3 plus 1 will become 4. So index 4 now is hold the variable start. So we will move the arrow start from index 0 to index 4. After move the start arrow, we will move the middle also. So we use again the formula middle equal to start plus n divided by 2. We use 4 plus 6 divided by 2 will get 5. So now the middle arrow must move from index 3 to index 5. So after changing the variable middle to index 5, we can check the value 60 with the target value also 60. We can conclude that we found the target. I already finished my part. I will pass the presentation to my teammate. Thank you.
Good evening, I am Choo Pong from BITP S1G1. Now I want to talk about quick explanation of binary search. Firstly, we have a function here with 4 parameters. Integer list is our array. Integer n is position of last element in the array, which is also means the array size minus 1. Integer target is our target that we need to find in array list. And last one is integer location we pass by reference, which record the location of target found in array. Then we declare 3 integers here. First mean first position in array, mean middle position in array, last mean last position in array. I want to mention here, these 3 integers hold the position of array but not value of array of that position. Then we set first equal to 0 and last equal to n. N is parameter that passed here just now. We have a while loop here. While first less than last, it will keep looping. Inside the while loop, we need to find the middle of our array. Therefore, we use mid equal to first plus last divided by 2. After that, we need to check this middle with target. If target is larger than element of middle, means that target is located in right hand part of our array. Then we start searching in the right hand part. We set first equal to mid plus 1, then search again. In other case, if the target is less than element of middle, the target should located in left hand side of array. Then we move our searching to left hand side. We set our last equal to mid minus 1. Then loop back again and search again. In last case, if middle element of array is exactly same with our target, then we found the target and just quit the loop. If target keep not in these 3 cases, this loop will keep looping until first is less than last. Loop will quit and means the target is not found in the array. After the loop, we set location equal to middle of array that found or stopped just now. And lastly, return true if found and return false if vice versa. Now I want to give an example. Let's say we have array here 17, 24, 9, 15, 70. And notice this is unsorted array. I want to mention here, binary search only work when array is sorted. Now we sort it and we want to find number 9 in array. We set first equal to 0, last equal to n. Go into the loop. Calculate middle 4 plus 0 divided by 2 is 4. So middle will be position 2 in array. Now compare element of array with target. Is 9 is larger than 17? No, then we'll move. Is 9 is smaller than 17? Yes. We set last equal to mid minus 1 here. Loop back again. Calculate middle 1 plus 0 divided by 2 equal to 0.5. Due to this is integer, so it will equal to 0. Middle is equal to 0 here. Compare with target. Now target is same with middle. We found the target. Quit the loop, store the location of middle and return result. Now we have another example here. We want to find 25 in array. Set first equal to 0 and last equal to 70. Calculate middle and get position 2. Set middle in 2. Compare element with target. 25 is larger than 17. So first equal to mid plus 1. Loop back again, calculate middle and get 3.5. Now off to 3, set mid equal to 3. Compare with target, 25 is larger than 24. So we set first equal to mid plus 1. Loop again, calculate middle and get 4. Set mid equal to 4. Compare with target, 25 is less than 17 now. So set last equal to mid minus 1. Now last is less than first. We quit the loop because target is not in array, record location and return itself. Okay, that's all from me. Thank you.
Hi, I am Jia Mei from S1G2. I will be covering using master method to derive the running time and discuss on complexity of binary search. The master method is a general method for solving or getting a closed form solution to recurrence relations that arise frequently in divide and conquer algorithms, which have the following form. Tn equals to AT times n over b plus fn, where a is the number of subproblems, b is the factor by which n is reduced, fn is the running time outside the recursion. The recurrence for binary search is Tn equals to T bracket n over 2 plus 1. This occurs by using master theorem. We only split the problem into another subproblem, so a equals to 1 and we divide n in half each time, thus b equals to 2. The running time outside the recursion which is O1, so fn equals to 1. Next, we compare the running time executed inside and outside the recursion. The runtime of the work done outside the recursion is O1, while the runtime work done inside the recursion given by this formula, in the end we will get O1. So, as the work outside and inside the recursion has the same runtime, so we are using second form of master theorem. Making the substitution, we will get the runtime of binary search is log n. Binary search has a worst case and average case running time of O log n, making O log n comparisons, where n is the number of elements in the array. The worst case occurs when a given target element is not in the list at all. This means the algorithm has halved the list again and again until it reaches a list of size 1. To get a list of size n down to a list of one element, log n divisions must be made. Each step of the binary search halves the search space. Binary search has an O1 best case running time. This occurs when the first midpoint selected is the target value. Binary search requires 3 pointers to elements, which may be array indices or pointers to memory locations, regardless of the size of the array. Therefore, the space complexity of binary search is O1. Given here is one example. From the example, suppose that L is a sorted list of size 1024. And we want to determine whether an item X is in L. From the binary search algorithm, it follows that every iteration of the while loop cuts the size of the search list by half. Because 1024 equals to 2 power 10, the while loop will have at most 11 iterations to determine whether X is in L. Because every iteration of the while loop makes 2 item key comparisons, that is, X is compared twice with the elements of L. The binary search will make at most 22 comparisons to determine whether X is in L. Thank you for listening.
Hi, my name is Loh Chun Ren. Now I'm going to suggest a better algorithm than binary search, which is called interpolation search. Interpolation search in short is an improved variant of binary search. This search algorithm works on the probing position of the required value. For this algorithm to work properly, the data collection should be in a sorted form and equally distributed, almost like binary search. Now let's talk about positioning in binary search. As we know that binary search always choose middle of the remaining search space, discarding one half or the other depending on the comparison result between the mid value and target value, while the remaining search space is reduced to the part before or after the mid position. In binary search, if the desired data is not found, then the rest of the list is divided in two parts, lower and higher, then the search is carried out in either of them. The diagram shown in this slide demonstrate how the positioning in binary search works. So let's look at the positioning for interpolation search, also known as position probing. Interpolation search finds a particular item by computing the probe position. Initially, the probe position is the position of the middlemost item of the collection. About this middlemost item is calculated using the formula given in this slide, which is mid equal to the lowest index of the list plus highest index of the list minus lowest index of the list divided by the value of the highest index minus the lowest index, then multiplied by the target value minus the value of lower index. By using this formula, they split the list into two parts. So if the middle item is greater than the item, then the probe position is again calculated in the sub-array to the right of the middle item. Otherwise, the item is searched in the sub-array to the left of the middle item. This process continues on the sub-array as well until the size of sub-array reduces to 0, which means no item is returned. So if a match occurs, then the index of the item is returned. In this case, since the target is equal to 2, by using this formula, we get the answer that mid is equal to 2, which is the target value. Now let's talk about the pseudocode of interpolation search. Interpolation search, so we have array list A, sign of A, which is the size of the array, and the target value X. First, set the lowest index to 0, LO, and a mid as -1, and then the highest index HI as n-1. Start a loop, which is with the condition of X does not match, means X does not equal to mid. Then if the lowest index is equal to highest index, or the value of lowest index equal to the value of highest index, which means that there's no more value inside the array. This means that the search is a failure, target not found, and if. So next, we set mid, the middle value, using the formula given. So if A mid equal to X, then the program will exit, success, target found at mid. If the mid value lower than X, the target value, then set the lower index to mid +1. If the mid value is higher than X, then set the highest index to mid -1. Continue to loop this process until it finish either exit failure or exit success. So the times and space complexity for both interpolation search and binary search are almost similar, except the average case. As we can see, the average case of interpolation search is O log n versus binary search O log n. This proves that interpolation search on average case is way more faster and efficient than binary search, and this is the reason that I choose this algorithm, as it is just way more efficient than the binary search. Thank you.